Hazel.
Hello, sister. So today we're going to look at some of the fundamental basics of geometry. We're going to look at triangles, squares, rectangles, some equations along with them, and just to get a basic view of geometry. So I'm going to assume that we know that geometry is the study of shapes and the equations associated with shapes, and they're also the equations that allow us to predict certain aspects of shapes. And this brings us to a division that we need to understand is the difference between a parameter and the area. Now, the parameter of an object is the length around the outside. That's the parameter. And you would simply add up each sides. The area, however, is the total amount of space within the object. To find the area, you can't simply add up the length of the sides. You have to use special equations, and it's these special equations that we'll be talking about. So before we get into those equations, let's look at some of the basics of shapes. We'll start with the simplest shapes. This is the square, and one of the things that we can predict about the parameter and the lengths of the sides of a square is that they're all going to be exactly the same. I've denoted that by putting an A on each one of the lengths here. A rectangle, alternatively, is going to have the same lengths, but in different horizontals. And I've denoted that by the A's for the lengths and B for the bases. And that's going to be true for any square or any rectangle you deal with. So if you're asked for the parameter of a square and you're given the length of one side, then you automatically know the length of all the sides. If you're given a rectangle and you're giving the length of the bottom side and one of the other sides, then you automatically know what the other side's lengths are. And in this way we can predict certain aspects of shapes, parameters, and areas without actually having the information using geometry. Okay, so let's look at this one. We've got a square, and I've given the length of one side as being 4. And if we remember from the previous slide that when it comes with a square, all of the sides are going to be equal. Therefore, we know that this side is also 4, this side is 4, and this side is 4. And to find the parameter, as I said before, we simply add all of the sides together. And in this case, the parameter of this square would be 16, because it's 4 plus 4 plus 4 plus 4. Okay, now let's see if we can do this one. This one's a little bit more involved. This is a rectangle, and we've given the length of one side, as the shorter side, as being 6. And we also know that the overall parameter is 30. Therefore, from this information, can we deduce what the lengths of the longer sides are? So take a moment, see if you can figure out how to do that, and then I'll walk through you with it. Walk you through it. Okay, so hopefully you figured this out. Now, if we remember the relations that the sides have from the previous slide, we know that this side here is also 6. These are the same lengths. And we know that if we add up all the sides, we should get 30 for the parameter. So, all we have to do is add these two sides together, which gives us 12. Now, to figure out these sides, we take 30 and subtract 12 from it, and that gives us the total of the sides, which is 18. Now that number we need to divide by 2 to get the lengths of the sides. If we divide 2 into 18, we get 9. Therefore, we know that the sides of each of these are equal to 9. Okay, now let's do one involving the area of a rectangle. So I've given the length of the long side as being 12, and we know that the area of the rectangle is 72. Therefore, can we figure out what the length of the smaller sides are from this information? Okay, so what we have to do is walk backwards. We have to recognize that area is equal to length times width. Therefore, we know the length is 12. We know that the area is 72, but we don't know what our width is. which is this value that we're solving for. And so what we would do, we could write that algebraically as 12w equals 72, divide by 12, and we would know that the width is equal to 6. Alright, let's move on from squares and rectangles to look at circles. Now, circles are different in that you can't look at their sides or their edges because they don't have a side or an edge. And so instead of looking for their parameter, you would solve for their circumference, which is the same thing as it was with parameter. It's just that the length around, like that. And to solve for the circumference of a circle, you use the equation 2 pi r. Now what that tells us is this r value is the radius of the circle, and the radius is determined from the center point here to the edge of the circle. This is the radius. Now you'll probably recall that the radius, if we say r squared, then we're referring to the diameter, which would be the entire length across the circle. Now you can also refer to it backwards, and if you're starting with the diameter and you want to refer to the radius, you can write it as d over 2, because essentially it's the diameter halved. So you can also, like with the previous shapes, you can study the circle's area, which as we said is the amount inside of the circle, and to do that you'd use the equation pi r squared equals area. Now you can also write that as pi times d equals a, d being the diameter all the way across, because remember we said just before that r squared is equal to d, and vice versa. And so that's how you would solve for the area and the circumference of a circle. Okay, so let's kind of put some of these concepts together into a problem. This problem here molds together the concepts of the rectangle with the concepts of the circle to give us kind of a tricky problem here that we can walk through, and I think it'll give you an idea of the sorts of geometry problems you're likely to encounter. This question actually comes straight out of the GRE book that I've been studying for, so I think it'll prove particularly useful for you. The question says the quarter circle with a center D has a radius of 4, and a rectangle, which is signified as A, B, C, and D, which you'll notice is the 4 points of that rectangle, has a parameter of 20, as I've indicated on the board. What is the parameter of the shaded region? So, first, let's look at the information that we have. So we know that the length, the total parameter of this rectangle is 20. And we know that the radius of this quarter circle is 4. Now, recall what the radius is, and it is the length from the middle of the circle to the edge of the circle, which would mean that this length here, which is from the middle of the circle to the edge, is going to be 4. Now that tells us something else about one of our edges that we might not notice otherwise. As if we notice, the same thing applies from D to E. We know that this edge is also 4. Now, if we use the rules that we learned with the rectangles previously, we'll know that if this entire length here is 4, then the length from A to B must also be 4, because they're equal to one another, so this is 4. Now we can have a pretty good idea of where to go from here. Okay, sorry for the interruption, I had a phone call. Alright, so back to our problem here. We know that the sides are equal to 4, and we know that from D to E, which doesn't include all the way to A, just from D to E, is also equal to 4. And our parameter is 20. So what we need to figure out is the lengths from A to D and from B to C. Now we can do some deduction here to figure this out. So if 4 and 4 together are 8, so let's write down 20 as the parameter, and let's say we subtract our widths from 20. That leaves us with 12. Now we already know that from D to E is 4, and we know that from B to C and from A to D must be some even multiple of 12. And so the only possible answer that we can think of is if we take 2 and divide by 12, because we have two sides, then it's going to give us 6. And 6 is going to be the length from B to C, and the complete length from A to D, 6. Now, this also gives us the length from A to E, because we would simply take 6, subtract 4, which is the length from E to D, and it would give us 2. So we know that this length is 2. Now we know the length from A to E is 2, from A to B is 4, and from B to C is 6. Okay, from here you'll notice that the only length that we're missing is the length from E to C. We have all the other lengths to find our area of the parameter of the shaded region. So to figure out the length from E to C, we're going to have to invoke some rules that we used in the circle previously. In particular, we're going to have to look at their circumference, which is going to be C is equal to 2 pi r. Now it's important to note that we're not actually dealing with an entire circle, we're only dealing with a quarter circle. So how can we make our equation reflect that? Well, we can simply multiply our equation by a quarter, or 1/4, and now our equation is applicable to this particular problem. So let's recognize that our radius, D to C, is equal to 4. So that's 1/4 times 2 pi 4. 4 times 2 is 8 pi times 1/4. 1/4 times 8 is 2 pi. And so now we know the length from E to C is 2 pi. Okay. That's a lot of work. Let's erase some of that, give us some room. And now to solve for the parameter of the shaded region, since we have the lengths of all of our sides. So we'll start with B to C, which is 6. And then A to B is 4, so plus 4. Plus A to E is 2. Plus E to C is 2 pi. 6 plus 4 is 10. Plus 2 is 12. That's 12 plus 2 pi. Now we could simplify that further if we wanted to, using the calculator and the value for pi, and we could get 18.28, and that would be the exact parameter of the shaded region. Okay, moving on now to probably the most important shape in all of geometry, and that is the triangle. Now, the triangles are important because we know multiple equations and patterns that are associated with them, and because most shapes that you'll encounter in geometry, even if they aren't triangles, contain a triangle, and that can potentially give you clues to the actual area or circumference or parameter of the shape that you're examining. And so there's lots of different kinds of triangles. We've got a couple of them here. The first one is the equilateral triangle. Now these are all based upon either their sides or their angles. The equilateral triangle has completely equal angles, 60, 60, and 60, all 60 degrees. Important thing. All triangles equal 180 degrees. That's an important thing to remember. Whenever you're trying to add up your sides, or if you're trying to figure out which triangle you're using, always remember that the triangle will never exceed 180 degrees. So the equilateral triangle have all the same angles, and the lengths of all the sides are exactly the same. The right triangle has many different incarnations, but the central principle is that it has one 90-degree angle, And then there's the isosceles triangle that has two equal angles at the base. And this top angle could be anything depending on what those two angles are. But the important thing is that these two angles are going to be exactly equal to one another, and the lengths of those sides there are going to be equal to one another. This bottom base will probably change depending on your angles. Now back to right triangles. A couple of important right triangles exist, and recognizing these patterns and ratios can help you predict angles or lengths of sides that you might not know, that the question might not provide you the information for. One example is the 3, 4, 5 triangle, and this one's here, and it's probably the easiest one to recognize because they're all going to be multiples of one another. For example, if this length here is 6 and this length here is 8, then you can recognize that this is a 3, 4, 5 triangle with a multiplier of 2. 6, add 2 more, you get 8, 2 more to that, and you know the length to this is 10. Without ever having to go through Pythagorean theorem or any of that kind of stuff, you can just predict it based on the ratios. The same thing is with this next one, is the 5, 12, 13. You've got one side that is going to be some multiple, and then two other sides are going to be very, very close as far as their range goes. And then the final one is the 1, 1 square root of 2, which I actually didn't write that. 1, 1 square root of 2. And their angles, the top and the farthest one here, are each 45 degrees with, of course, the 90-degree right triangle. Now, a way you might notice this, for example, is if you see something like a 3 here and a 3 here. They give you this triangle, and they say, what is the length of the side here missing? Now, you know from that, since these are both 45-degree angles, and this length is 3 square root of 2 and this length is 3, I mean, you can not even know that. If you know that they're both 45-degree angles and you've got 3 square root of 2, you've got all the information you need, because you recognize that this is the ratio 1, 1 and square root of 2, so these sides have to be 3. And now, of course, you could have solved that without knowing the ratios. You could have solved it with Pythagorean theorem. It's just that this is quicker if you can recognize the ratios and help you get through it faster. But so let's move on now and actually look at Pythagorean theorem and how to use it, because chances are if you don't recognize these patterns, that'll be what you'll be using. Okay. So let's say we have a right triangle with the hypotenuse, which is this long side, as 26 and the base is 24, and we want to know what the height of the triangle is. We'll call that value x. So how do we solve for that value if we don't immediately recognize any kind of ratio, such as in the previous problems? Well, we could use the Pythagorean theorem, and that is a squared plus b squared is equal to c squared. Now what that means is that this value here is a, this value is b, and the hypotenuse is always the value c. So anytime you see a triangle and you don't immediately recognize a ratio, this is probably how you're going to solve for a missing side, is using this equation. So now you just take those values and you plug them into the equation. Now we don't know what our a is, that's the value we're solving for, but our b is 24, so it's a squared plus 24 squared equals the hypotenuse, which is 26 squared. And so now we know 24 squared is 576, 26 squared is 676 plus a squared. And now we can subtract 576 from 676, and that gives us a squared is equal to 100. And now to get rid of the square, we take the square root of each side, which gives us a is equal to 10. And so in that manner we solved that the value for x here is equal to 10. Now, if you took a moment and look, you'd actually see that there is a ratio, that this triangle here could have been predicted without using the Pythagorean theorem. recognizing that the bottom is 24 and the top is 26, we know that both of these are multiples of 12 and 13. And they're each multiples of 2, and 12 and 13. And therefore, we could have said that this is a 5, 12, 13 triangle. If we recognize that this is the case, then we know that our last problem, since these two are the multipliers of 2, you multiply 2 by 12, you get 24, 2 times 13, you get 26. We could have just multiplied 2 times 5 and recognized right off the bat that that's 10. And that would have saved us all of this work here. But just in case, sometimes it's not that obvious, but just in case, that's always a good option to go if time is of the essence. Okay, so now let's do a word problem involving geometry and triangles. This one is also straight out of the GRE book, but it's a pretty simple one, and though you can't see the words, I'm going to write out all the information onto the board so you'll be able to walk through it. The question reads, a ladder 20 feet long is placed against a wall. If the distance on the ground from the wall to the ladder is 12 feet, how many feet up the wall does the ladder reach? So, let's see if we can get a picture of this. I think that always helps. So this is the wall and here's the ground. And it says the ladder is 20 feet long and it is placed against the wall. So here's our ladder. It's a pretty ugly ladder, but it's a ladder. And the ladder is 20 feet long. And it tells us that the distance on the ground from the wall to the ladder is 12 feet, which is this distance here, is 12 feet. How many feet up the wall does the ladder reach? So it's asking us for this side. Now looking at it like that, it becomes a pretty simple right angle geometry problem. And we can apply the Pythagorean theorem. A squared plus b squared equals c squared. This is, recognize that this is our A, this is our B, and this is our C. A squared plus 12 squared equals 20 squared. A squared plus 144 equals 400. And a squared minus 400 from 144 gives us 256. We're going to take the square root of 256 to get rid of this square, and that gives us 16. Therefore, we know that the length of A is 16 feet. And that's how you would solve that particular word problem. Okay, so in this module we looked at squares, we looked at rectangles, we looked at what the perimeter and the area are, we looked at circles, and we looked at different kinds of triangles, and we did a problem where we kind of mold some of them together. Worked out a lot of problems this time around. There's still a lot more geometry type things we can do. Some other shapes that we can go through, some more complicated geometry problems we can look at. I just wanted you to see this to get a feel of whether it was not in depth enough, whether you want me to go more in depth, and just let me know what you thought of it. I hope it helped, and
Bye, Lulu.